if on this website you can pick up like the previous classes here. So remember I showed you this on the first day. You can find the 19th of August and the 17th of August. So I'll post all of our classes on that as we go along. Any big plans for this weekend? It's Friday. What's the goings on this weekend? Today at 4, who are you playing? Okay, great. Soccer game at 4 on the field right there. Anything else going on this weekend? Any big events? Anybody getting married, having a baby, anything like that? No? Okay. I think this weekend, we have a pretty typical weekend. Kids want to have like a play date, is that what they call it, with some friends of theirs. We'll probably go for a bike ride. We go grocery shopping. I think that's about it. That's exciting, huh? I mean, an exciting life. All right. Pretty easy stuff so far, I think, right? What we've been doing, unit analysis, stuff like that, dimensional analysis. Yay, easy stuff. Going to do a little bit of review today for trig and calculus, and then we'll start on chapter 2. As I said, in this class, we'll use, throughout the semester, we'll use calc 1, 2, and 3. But the calculus that we use is pretty simple, and I'll show you what we do. We're just going to do some simple derivatives, some simple integrals, and then we'll do a little vector calculus towards the end, cross products, dot products, okay? But again, I know most of you are either in Calc 1 or have just finished Calc 1, so don't sweat it though. I'll give you everything that you need. We're not going to do hardly any of the stuff that y'all do in calculus, just simple derivatives and integrals. Let's see, I forgot to pull up the classroom registration, but if you're not yet registered your clicker, listen, I'll pull it up on Monday. I'm not too worried about it. Whatever you click in today will be registered to your name as soon as we get you registered. Okay? All right, we left off last time with order of magnitude and estimations. We're going to pick up now with coordinate systems and then trig. We'll do a lot of trig this semester because we'll be dealing with vectors a lot. So a lot of right angle trigonometry mainly. So most of you probably didn't take trig in college, you had it in high school, but we'll just do sort of the basic right triangle stuff. I'll review that today. Hey, Gary. All right, so we'll use two different types of coordinate systems. The first is the Cartesian coordinate system, which I'm sure you're familiar with, x, y, and z coordinates. Later, we'll also use I, j, and k notation when we get into vectors to represent those directions, the x, y, and z. We'll see that in the next chapter. This is an xy coordinate system. Typically, to the right as a positive, to the left as a negative, because we use a right-handed coordinate system, because we live in a right-handed world, right? And typically we'll have negative y is in the downward direction, positive y is in the positive direction. In the z-axis, we'll take out of the board to be the positive z direction, and into the board or into the page to be the negative z direction. I draw my z's kind of funny. They have a little line in them. That's to show them apart from 2. So just get used to it. Yeah, so there's our 3-dimensional coordinate system. We'll use these a lot. We'll also use a plane polar coordinate system, not quite as much as the Cartesian coordinate system, but in a plane polar coordinate system, instead of using x and y coordinates, use r and theta. So r is just the distance from the origin. This is our value r, and then theta is the angle measured from the x-axis. Okay, y'all have used plane polar coordinate systems before? You can define a point, any point in space with that. In 3 dimensions, which we won't use in the plane polar coordinate, you can do that as well. You just have another angle to define where that point is. But we won't use it in 3 dimensions. All right, so this is where our trig comes in. Basically, we're going to be dealing with right angle triangles like this one. We have our hypotenuse here. The hypotenuse is the side opposite the 90-degree angle. And then we have the x and the y. Typically, we call this side, which is opposite the angle theta, that's our opposite side. And then this side, which is adjacent to the angle, is our adjacent side. But notice that if we define the angle differently, then these two become switched. This would be the opposite side, and this would be the adjacent side. All right, that's important because that's how we define our trigonometric functions, our sines, cosines, and tangents. You have this mnemonic. Some of you might have learned this in different ways. How did you learn it? You just memorize. But what's the mnemonic? It's like, I just say SOHCAHTOA. What do y'all say? Whatever, SOHCAHTOA. This is just tells you what these trigonometric functions are. So for example, the sine of your angle theta is equal to opposite over hypotenuse. The cosine of your angle theta is adjacent over hypotenuse. So sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and then the tangent of the angle theta is opposite over adjacent. All right, sine, opposite hypotenuse, cosine, adjacent hypotenuse, tangent, opposite over adjacent. You'll need to know those definitions. We'll use them a lot throughout the semester because we're dealing with vectors all semester. All right, and whenever we're dealing with vectors, we'll have to know those right angle triangles. Also, we know that the sides of the triangle are related by the Pythagorean theorem. That is that x squared plus y squared is equal to r squared. All right, y'all seen this before? We have some special triangles. One that I like to use especially is the 3, 4, 5 triangle. So if I have a triangle and this side is 3 units long, this side is 4 units long, and then this side is 5 units long. And let's see, this angle, does anybody know what this angle is? We can find it, right? You can, if I want to know this angle, I just say that the cosine of theta is equal to, what would the cosine of theta be in this case? 4/5, right? And so if I want to know that angle theta, I would say theta is equal to the inverse cosine of 4/5. Can somebody tell me what that is? Or everybody, just try this out. Make sure that you can do this calculation. You'll need your calculator in degree mode, unless you'll need it in degree mode all semester. Towards the end, if we get into oscillations, I don't know if we'll get into that this semester, you'll need it in radian mode, and I'll tell you. What is that angle, somebody? 30, I was going to call it 37 degrees, right? So it is 37 degrees. And then that would make this angle up here what? If this angle is 37 degrees, what must this other angle be? 53, yeah, if it's 37, 53 degrees. Because we know that those two angles have to add up to equal what? 90 degrees. Know your right triangles, okay? If you don't know them, please come see me because you're going to use them a lot. All right, your Pythagorean theorem, your trigonometric functions describe how the angles are related to the sides of the triangle, and then also the sum of all the angles is 180. Since you have a right angle in there, the sum of those two angles is 90 degrees. All right, often with the angle theta, with the problems that you'll be doing, you'll be using the tangent of the theta. So here, for example, I could get the same answer just by saying tan of theta is opposite over adjacent, TOA, right? So the tan of theta is 3/4, and then theta would be the inverse tan of 3/4. If you do that in calculator, you can try it if you want, but you get the same answer, 37 degrees. Okay? Let's try a little quick test here. So this figure, what is R is the first question, and then what is theta is the second question. Is R 6, 4.3, or 19 meters? These are the x and y coordinates for that in plane polar coordinate system. Or excuse me, these are in the Cartesian coordinates, these are the x and y coordinates. And now I'm asking you to express it in the plane polar coordinate system. First question is just what is R? If those are my coordinates, what is the value for R? If you finish this, go ahead and do the next question. I'll pull up the clicker for that in just a second. First, what is R? We are doing that. I'm going to step out. I'll be right back. You are doing pretty well on this. We'll just do about 10 more seconds. Let's say 2:15. We'll stop. And tell me, what is R? 2:15. About 5 more seconds. Remember, if you don't know the answer, just guess. Okay, excellent. B is the right answer. With this, you're just doing the Pythagorean theorem. First thing you want to do is recognize that there is a triangle here. It looks like this. This side is 2.5. That's my y coordinate, and this side is 3.5. And I want to know what is this angle, or what is that side. And so I just say the square root of 3.5 squared plus 2.5 squared, and that's equal to 4.3. You're doing this a lot, okay? So if you're having trouble with it, I think most of you are okay with it, but if you're having trouble with it, please come see me, and we'll sit down and go over our right angle trigonometry. So B is the right answer. Now I also want to know, what is the angle theta, and also be aware of how this angle theta is measured from there. What is the angle theta? Is it 324, 36, or 216? I'll write these angles up here. So you can see them. 324, 36, or 216? Let's do about 10 more seconds, y'all. I'll stop at 45. 45. Okay, excellent. C is the right answer. Listen, you don't even need to calculate that, right? Because you can just look at it and tell what the right answer is if you know your quadrants. Remember, with our quadrants in Cartesian coordinate system, what is this quadrant right here? This is the first. What about this one? That's your fourth, right? It goes 1, 2, 3, 4. I start here at 0 degrees. I have 90 degrees here, 180, 270, and then I go back to 360. Or if you're talking about in radians, it goes 0, pi over 2, pi, 3 pi over 2, 2 pi. We won't use radians until we get to oscillations, though. So we'll mainly talk about it in terms of degrees. So you could pick out the one that's in the third quadrant, which is between 180 and 270, which would be C, 216. The way we'd go about calculating this is you would look at our triangle, which is here. I want to find this angle, I'll call it phi, right? If I want to find that angle phi, I would say the tangent of phi, gosh, what would it be? That's right, opposite over adjacent, which is going to be 2.5 over 3.5. You can put the negatives or not, it doesn't really matter, they go away anyway. And then I do the inverse tangent of that, and I find that phi is equal to 36 degrees. So if this is equal to 36 degrees, that means that this is 180 plus 36, which is 216. Okay? I think that's probably a review for a lot of you, but you're going to use it a lot this semester, so make sure that you got it. All right, let's look a little bit at our calculus. We're just going to do some simple derivatives and integrals. First of all, the mathematical definition of a derivative looks like this. It's just the limit as delta t approaches 0 of this function, delta x over delta t. And so if we look at a graph of x versus t, so let's say this is a graph where we plot x, the variable x here, and the variable t here. The derivative is just the slope of that graph at a particular point. Right, this is just slope of this graph, right? How do we define what slope is? It's what over what? It's just rise over run. So the derivative is just a glorified way of saying it's the slope of a function, or the slope of a graph. So we're looking here at the slope, and what this limit tells us is that we're letting this number get really, really small. And so what we're doing is instead of, we'll do this a lot in the next chapter, instead of looking at the slope, say, between these 2 points, where this is delta t, say from the final time to the initial time, we're collapsing it down to a particular point. We're letting that delta t get very, 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 very small so that we're taking the slope at a particular point on the graph. Okay? So the derivative is just the slope at a particular point. And so, for example, on this graph, we could represent that by drawing a line that looks like this. We call this a tangent line. You'll have to do it in the next chapter. It has a mathematical definition, but basically I like to think of a tangent line as sort of resting on the function. We'll get into that next chapter, so let's not worry about it too much. But the derivative is just the slope of the function at a particular point. Yes? Y'all in calculus right now? Y'all got into the definition of a derivative yet? Or are you just doing limits? Still doing limits. They had it in high school, huh? Right? Calculus in high school. Okay. Listen, the derivatives that we'll do will be pretty simple. We're just going to do simple polynomials. If you haven't seen them, let me show you. They're really easy. So let's say that I have a function of x with respect to t, like the function bt to the n. So for example, it might be 3x squared, where b is equal to 3, n is equal to 2. And I want to take the derivative of it. The derivative of this function is going to be b times n times t to the n minus 1. So if I have 3x squared, or let's make that 3t squared just to make it consistent. If I have 3t squared, what would be the derivative of this function? Right, it would be 6t. I would say 3, which is b, times 2 times t to the 2 minus 1. You'll get really good at this. It's pretty simple once you get the hang of it, okay? You just multiply the exponent by the coefficient, and then you reduce the exponent by 1. So this function would be x equals 6 times t. We'll do a lot of derivatives, but most of our derivatives are just going to be simple polynomials. Later we'll get into derivatives of trigonometric functions, but they're pretty easy too. And then later we'll see the chain rule when we get into those trig functions. But again, pretty simple. So if you're in calculus right now, don't sweat it. These derivatives are really simple, the ones that we'll be doing. All right, we'll do another quick example. Let's say that I have let's do a different number. Let's say 1/2 t to the minus 2. Try that derivative. What do you think that derivative is? Let's try it on your own. Remember, I take my exponent, multiply it by the coefficient. That becomes my new coefficient, and then I reduce the exponent by 1. All right, so what's the derivative of this function? That's right, negative t to the negative 3. Negative 2 times 1/2 is a negative 1. Negative 2 minus 1 is negative 3. All right, let's try this little quick test. You're not going to see quick tests like this on your test. Well, I don't know, you could see a multiple choice question, but we'll get into derivatives. You'll have derivatives on the next test. So what is this derivative? All right, just about. I'll stop at 30, about 5 more seconds. Excellent. Great job. Did I tell you the cow joke? The cow's joke? I did tell you that one. What's the worst part about living on O Street? First of all, this is a potty joke. I'm sorry if you're offended. Okay. But what's the worst part about living on O Street? I don't know what. You gotta walk a whole block to pee. I'm sorry, are you offended? That's not offensive. Okay, good. All right. Let's see. Let's go ahead and give you the derivatives of our sine and cosine functions. Oh, no, I guess we are doing the chain rule here. So d du, the derivative of the sine function is just going to be the cosine function. And the derivative of the cosine function is just negative sine. It's the negative of the sine function. We won't get into that until later, and we'll review that again soon, or when we get to it. Sometimes you'll need the chain rule. Chain rule is a really useful rule. Like in calculus, you don't learn a whole lot of useful stuff, but the chain rule is one of those things. So when you get to calculus, make sure that you master the chain rule. It just says that if I have the derivative of a function with respect to t, that this is equivalent to dx du times du dt. See, those two are equivalent. I can imagine that I get rid of these du's and I'm left with the same thing. So those two expressions are equivalent. So let's say, for example, that I want to take the derivative of this function, this 2 cosine t squared plus 3. The first thing that I'll do is I'll let the operand of the cosine function be u. So I would let u equal t squared plus 3. Right? So then I could rewrite this function as x equals 2 cosine of u. I just made that substitution. Pretty simple substitution. And then I can apply my chain rule. I say dx dt equals dx du times du dt. This is just the chain rule. I know this is true because it is true. And then I have, first of all, the derivative of x with respect to u. That's going to be the derivative of this function with respect to u. So it's going to be d2 cosine of u du. And then I take the derivative of u with respect to t. Have I lost y'all? Are you with me? Okay. I take the derivative of u, so that's going to be the derivative of t squared plus 3 with respect to t. And when I do those two derivatives, that will be the expression for dx dt. All right. Now the derivative of 2 cosine, the derivative of a cosine function is just going to be negative sine. So I'm going to have negative 2 sine of u times the derivative of this function, t squared plus 3. I just break this into two parts. The derivative of t squared is what? 2t. 2 times 1 times t to the 2 minus 1. That's just 2t. And what's the derivative of 3? Is 0. Listen, a derivative tells how much an expression is changing with respect to that variable. With respect to time, this expression is not changing at all. So anytime I have the derivative of a constant, its derivative is 0. A derivative tells how something changes, and this is not changing, so its derivative is 0. You can also think of it as this is the same as 3 times t to the 0, because t to the 0 is equal to 1. So 3 times t to the 0, your derivative would be 0 times 3 times t to the negative 1. But any number times 0 is 0. So that derivative is 0. So here I'm just left with 2t. All right, and then I can substitute back in. I have negative 2, let's see, what did I call u here? 2 squared plus 3. It was t squared plus 3, yeah, times 2t. And then that's the answer. Again, we won't use the chain rule. If this confuses you, just sort of set it up on a shelf. and we'll revisit it later in the semester, or maybe even next semester, I forget. We won't use the chain rule for some time, okay? And hopefully by that time you'll have had it in calculus. But just sort of give it here as review for many of you, are new for some of you, I understand. Okay? It's exciting stuff, right? Calculus changed the world. You know who invented calculus? Who came up with it? Who? Isaac Newton, right. There's another guy too, y'all know his name? I think it was like Leibniz or something. He's not as famous, but like they came up with it on separate continents at the same time. It's pretty cool. But it really changed the world. It allows for buildings, it allows for engineering feats, it allows for wireless communication. Really everything that we do in physics is based on this simple idea of calculus. Changed your world, rocked your world, as you might say. Okay? One of the greatest discoveries ever. Okay, let's look a little bit at integrals. Derivatives give the what of a function? The slope of a function. Integrals give the area of a function. All right, derivatives give slope, integrals give area. So we define our integral. Say I have some function f of x, whatever it is, and I want to take its integral with respect to x. I define this, your mathematical definition is a limit as n approaches infinity. I'll explain what all these are in just a second. Of the summation from I equal 1, or excuse me, I equal 1. I is just a counter. It's going from 1 to infinity of actually, let's not worry about that. Let's not worry about the counter. We'll just say that it is the limit as n approaches infinity of f of x times delta x. So if I have a function here, what this is saying is I'm going to take this function. This is my f of x. It has a certain value on the y-axis, and I'm going to multiply it by the width of these cells, or these blocks that I divided into. I'm going to divide it into an infinite number of blocks. That's where this n approaches infinity comes from. I'm going to break it into those blocks, and then I'm going to multiply it by the height. So I'm breaking this into its separate sections. I'm going to draw a big one. I break it into these blocks, and I multiply the height of it by the width of it. All right, so I multiply the height of my block by the width of my block. And then I add up all those. That's what the summation symbol means, is I'm adding up the area of each of these individual blocks. And by the way, I'm giving an infinite number of blocks, so I get a perfect representation of the area underneath that graph. Okay? So integrals, in short, are just the area under the function. We're not going to do numerical calculations, but some of you going into engineering or maybe even in chemistry you might do this, where you have to numerically find the integral of a function. It's really easy to do. Let's say that I have this function right here, and I want to know the integral of it. I just go through and I calculate the area of these blocks. They're pretty simple algorithms to do this. You can probably download them online, but they're very simple to write, where I just set a bin size. I determine how big is my bin, and the accuracy of your calculation will be dependent upon your bin size. What do you want to make your bin size, bigger or smaller to make it more accurate? Right. You make that bin size very, very small in order to give a more accurate integral, and then you just go through and you add them up. And that's really easy to program. So to find numerical integrals is pretty simple. Any math majors in here? No? Like one of the best classes I ever took was where I learned how to do this, was called Numerical Analysis. If you're going into grad school and you expect to do any sort of computing, I really recommend that you take that class. They offer it here at Nichols, Numerical Analysis. And in that class, they combine algorithms and computer programming and allow you to do things like this, where you find integrals numerically. You can do derivatives similarly. Okay, now when we're dealing with polynomials, which is what we'll do in this class, if I want to find the integral of a polynomial, the integral of, say, x to the n dx is just going to be 1 over n plus 1. times x to the n plus 1. So for example, if I give you some numbers here, let me see, I think I might have it on the next page. Where I got that x to the n plus 1, 1 over n plus 1, x to the n plus 1. All right. So say, for example, I have this, the integral of 3x squared. How would I find the integral of this, or what would be the integral of this function? All right, it'd be x cubed, because I would have 1 over n plus 1. Now n is equal to 2. So 1 over n plus 1 would be 1 over 2 plus 1 times x to the n plus 1. That's going to be 2 plus 1. And then I have this other 3 out here, which is just a coefficient. So this 3 cancels with this 3, and I'm just left with x cubed. Let's try one other one. Let's say that I want to take the integral of 4t to the minus 2. What would that be equal to? The integral of 4t to the minus 2, and I'm doing this integral with respect to t. Just take a second, then I'll write the answer on the board. All right, so I would do, I'm going to write my 4 first. It doesn't change. I have 1 over negative 2 plus 1 times x to the negative 2 plus 1. And so that's going to be negative 4 over 3, or excuse me, this should be a t, sorry, times t to the negative 1. Oh, yes, you're right. I'm sorry. I'll fix it here in a second. So this should be t to the negative 1. Because negative 2 plus 1 is negative 1. All right? Okay, we'll see integrals in the next chapter, but they're just going to be simple polynomials, and you'll get some practice with them if you haven't seen them before. So this typically isn't covered till Calculus 2, but we'll see it this semester. All right, let's look at this graph. You'll have some questions. Yeah. Negative 4 over 1. Okay, well, I have 4 times 1 over n plus 1 right here. And so this negative 2 plus 1 is equal to negative 1. And so that gives me a 4 over a negative 1. Done that correctly, right? Yeah, so I get negative 4 times t to the minus 1. Is that clear? Everybody else clear on me? Clear with me? Sorta, kinda. Listen, if you want to sit down with me and we can go over derivatives and integrals, or you can just wait. We'll get into them in the next chapter, and we'll get some more practice with them, and you'll be able to do it a little more easily. I find that once you do it a few times, it's just like second nature. Now let's look at this graph. This is a graph. The function is v equals 2t squared, and I just want to estimate the area under this graph from t equals 0 to t equals 5 seconds. So you'll likely have a question like this on the next exam where I just give you some function and its graph, and I ask you to graphically represent either the integral or the derivative. Now the integral is the area, right? So I want to take the integral of this function. So I want you to estimate the area under this graph. That is everything from 0 to 5 that falls under this graph. You'll do this in lab as well in a couple of labs. How would you go about estimating that area? Count the rectangles, right. So each of these rectangles has how much area? 10. I want to look at my units too here, right? Because to get the area, I multiply the y times the x. So I'm multiplying meters per second times seconds. So what are going to be the units of the area? Meters. So that should give you some insight as to what it is that we're measuring. We're measuring here not a speed or an acceleration, but a position or a distance that's traveled. So here, what is the area of the rectangle? Somebody say? It's 10 meters, right? Because I have 1 unit here and I have 10 units here. So each of these rectangles is 10 meters. Each rectangle underneath the line represents 10 meters that's been traveled by this object. So let's see, I'm just going to count them. I have 1, 2, 3, 4. I'm going to count these two together as 5. I'll count this one as 6. This one is 7. And then I'll count these two together as 8. So I'm getting roughly about 80 meters. So if I estimate that area, just adding up the rectangles, I get 80 meters. Now, I also want to calculate the result of the integral. So I know the function here. My function is 2t squared. So I want to take the integral and calculate that value, actually what it should be. So I do the integral of 2t squared dt. And here we're actually going to evaluate this integral over two limits. What are my limits for this integral? 5 and 0. So I'm going from t equals 0 to t equals 5. When you write the numbers on the top of the integral sign, that's what that means, that you're evaluating the integral over limits. Well, let's first just take the integral. What is the integral of this function? That's right, 2/3 t cubed. Remember, this is n, so I get 2 over n plus 1. That's going to be 2 plus 1 times t to the n plus 1. That's 2 plus 1. So I get 2/3 t cubed. And then I would further write this, evaluating it at my limits. Something like this. I would say t equals 0 to t equals 5. Then I would just plug in, you can go to the next page if you like, but I'm going to write it here. Plug in those, evaluated at those limits. I have 2/3 times 5 cubed minus 2/3 times 0 cubed. And that's what it means to evaluate it at those limits. This works out to have a value equal to 2/3 of 125, which is 83 meters. Which is awfully darn close to what we did just graphically. All right. But this is more accurate. Okay, you with me, folks? Don't worry, this is all review. We're going to see it again. So you have a quick test. What is the integral of this function? Is this one we did before? Similar? Okay, what should be? Remember, you can ask your neighbor if you like what they get. All right, I'm going to stop and at 120, 120. Just guess if you don't know. Okay, A is the right answer. Very good. Remember here, our n is equal to -2. And so it's going to be 3 over n plus 1. I'm sorry, what was the answer? A, yeah. Okay, 3 over n plus 1. I'll try to put the wrong answer. Times t to the n plus 1. So this is going to be -2 plus 1 times t to the -2 plus 1. That's going to be -3 times t to the -1, which is -3 over t, which is A. Okay, that's really exciting. Like, y'all look excited about this. Are you? Not really at all? Okay. All right, let's go on to chapter 2. Although you'll find in your book there are some homework problems. So for example here, Just to remind you, in this chapter we've covered standards of measurement. You'll see those on exam 1. We've covered estimations and order of magnitude. There's some problems here. Also, if you look back at old tests, you'll find problems as well that are practicing that. What else have we done? We've done trig. We've done dimensional analysis, looking at equations and figuring out if their units match up right, and then also conversion of units, trigonometry review, and calculus review. That's all of this chapter, and you'll see that on exam 1. Right, and there's also stuff that we'll use all semester. Any questions from chapter 1 before we move on? Any areas that you're really concerned about? Any areas that you're particularly excited about in chapter 1? You don't really care at all? Seriously? No? Okay, well let's move on to chapter 2, and we'll start applying some of these things in chapter 2 and in chapter 3. Guys, listen, you want to be spending about a half an hour a day. Half an hour a day is probably a pretty good estimate for the amount of time that you should be spending on all of your classes. Really, they say that you should, for every hour that you spend in class, you should spend another hour outside of class. But I think a half an hour a day is a pretty good estimate. So with this class, the way that you could be spending that time is working through the homework and practicing the old exam questions. That's really the best way to be prepared for the exam. I know that a lot of you will put off preparing for the exam until when? The day before, right? Not many of you, but some of you will. That's not a very good practice, and generally students that do that don't do very well in the class. So I'd recommend that you start this week, if you haven't already, just setting aside a half an hour a day. 5:30 to 6, 8:30 to 9. You get up at 3 o'clock in the morning and do like 3 to 3:30 or whatever. But find a half hour a day and just sort of carve that into your day and make it a priority. Don't watch whatever it is that you watch for half an hour, and instead work some physics, right? Just doing a little bit every day will help you a lot. Okay? Is that what y'all do? That's what y'all are good students, so I think that's what you do already, right? Shane, that's what you do? Yeah. Steven, you do that? Yeah. Okay. Brooke, you do that? No? No. Okay. It's just a good practice for you to get into. This first chapter is on motion in one dimension. We're going to spend the next 2 chapters on motion. Probably that'll be our exam 1. Chapters 1, 2, and all are part of chapter 3. But this first chapter is on motion in one dimension. Kinematics, this describes motion. It's the study of motion. People have been doing this for hundreds and hundreds of years. Galileo did this, Newton did this. When we're talking about motion of an object, we need to think about the frame of reference. The frame of reference sets the coordinate system. And the origin from where you're observing the emotion. All right, so we'll do that. In every problem that we encounter, we'll set the coordinate system and set our origin. And in most problems, it's going to be really obvious. We won't get so much into relative motion, that is, how things move relative to one another, although we will sort of touch on that a little bit. Though there was, I saw this, you ever listen to Minute Physics on YouTube? Isn't that a cool show? Did you see the one about immovable versus, yeah, that was pretty cool, huh? He talked about how there is nothing that's immovable. There is no object that's not movable because all you have to do is move with respect to it, and it looks as if it's moving. So, like, for example, right now, y'all are basically immovable, right? But if I move like this, it looks to me like y'all are all moving around. Like if I shift across the room, right now you're all sort of shifting around in the room. That's kind of weird, huh? Yeah. But you can watch that on Minute Physics. We're not going to watch it here. It's all about your frame of reference, where you're watching the motion from. In kinematics, we're going to define several different things. They all build on one another, and they're all related to one another. The first is displacement. And in this first part of this chapter, we'll go through and we'll define each thing and how it relates to the motion of an object. The next is velocity. And then finally we have acceleration. If you've had this before, and many of you have, I suspect, you'll notice that each of them is the change in the other. So, for example, displacement describes how far something's moved. This describes how much this changes with respect to time. So how does displacement change with respect to time? And acceleration describes how velocity changes with respect to time. All right. Coincidentally, they're also all what of one another. They're all derivatives of one another. Velocity is the derivative with respect to time of displacement. Acceleration is the derivative of velocity with respect to time. So we'll see that when we define each of these. You might know what the change in acceleration with respect to time is. This is just an interesting little tidbit. It's kind of cool. Like, you would be cool if you knew it. Yeah. Who knows what acceleration over time is a measure of? No, it's not speed. No, acceleration times time is speed. But the derivative of acceleration with respect to time. Nobody knows? That's because, like, I'm the only cool person in this class. It's jerk. It's a physical quantity. It's called jerk. How the acceleration changes. Isn't that cool? So next time somebody calls you a jerk, you can say, no, that's just how the acceleration changes with time. All right. I know people don't call y'all jerks. Displacement's pretty simple. I have delta x is our displacement, and it's just the difference in the final and the initial position. So xf is the final position, xi is the initial position. Let's see, I have a Seabiscuit clip. I think I have it. Let me make sure. Yeah. Well, I have Seabiscuit. He's going around this track. It's about a mile long, right? And I have this horse. And he goes around the track, and he comes back. What is his displacement in that case? It's 0, right? He travels a mile, and we would say that his distance is 0, but his actual change in position is 0 because he starts at x equals 0 and he finishes at x equals 0. So he has 0 displacement here because he's coming back to his original position. Let's see. We got 8:20, right? I think we'll just stop there. It's a little bit early, but y'all have a great weekend, and I will see you on Monday